What you're about to learn is used all the time, from other courses you take to your everyday life. You're about to begin to learn how to predict what will happen to an object when it falls, collides, accelerates, and more. Look around. The world is full of moving objects. Think of sports, transportation, military. Even as you sit in your chair right now, you are hurtling around the sun faster than you can imagine. In this video, we will look at how things can move back and forth in a straight line, and this is called one-dimensional kinematics. Let's start by looking at a red plastic ball. Right now, the ball isn't moving, so we can say it has constant position, denoted by x. Let's call this point the starting point, or position equals 0. We can use this ruler to keep track of position. Although the ruler uses centimeters for its units, the rules you're about to learn apply no matter what units we choose to use. If we drop another ball somewhere else, we can compare the locations of the two balls. This new ball has a constant position equal to positive 5 centimeters, because it is 5 units to the right of the origin, at 0. And since we've set up the ruler so that balls to the right of 0 have positive position, this means that balls to the left of 0 will have negative position. So let's define position as the number describing the location of an object compared to the starting point, which we can choose. But what about if we want to move the original red ball to a new position? To do this, we'll have to talk about a few new ideas. Distance tells us how much ground the ball has covered since it started moving. Notice how any movement of the ball adds to the distance. Displacement tells us how far the ball ends up compared to where it started from. Look at how when the ball gets closer to 0, displacement goes down, but distance is always increasing. So we can see that the distance tells us how far we have traveled, but gives us no information on where the ball is at any time. While displacement tells us where the ball is, but on its own doesn't tell us much about how far the ball has really traveled in the past. The differences between displacement and distance are so important that scientists came up with 2 words to describe these differences: scalar and vector. Distance is a scalar because it is just a number, and it only tells us how far the ball has gone without any info on which direction it moved in. A scalar is just a magnitude. Displacement is a vector because we can tell the difference between when the ball has moved left or right. The vector quantity tells us both magnitude and direction. Here's a trickier one though. What about position? Well, first let's ask ourselves this: does position have a magnitude? This one's a bit of a freebie. Position is represented by numbers, so of course it has a magnitude. But what about direction? We have to think carefully. We know that position can be a negative number too, and we already saw that negative means left in one dimension. So then position has both a magnitude and a direction, so it has to be a vector. Okay, so when we are dealing with one dimension, it can be hard to tell the difference between a scalar and a vector. So let's quickly take a look into a 2-dimensional example. Imagine a runner going around a track. As the runner goes around, the total distance is simply the length of ground the runner has covered, and is shown here in green. The total displacement is the straight line change in position from where the runner started, shown in blue. We don't need to show the exact numbers here, it's just the length of the lines that matter. In one dimension, we usually just keep track of the direction of the displacement with a positive or a negative sign. In 2 dimensions, we can use angles, compass directions, and more. After the race, the runner has traveled a distance of 1 lap, or 400 meters. The displacement of the runner, however, is 0, because the runner ended up at the exact same position as it started at, so there is no change in position after 1 lap. Now that we have a clear picture of distance and displacement, we can get into some juicier ideas. If we want to change the position of the ball, time needs to pass, and with all this background theory, we can now look at the idea of velocity. In day-to-day life, you have probably heard people talk about the speed of an object rather than its velocity, but what's the difference? Well, speed is a scalar quantity, while velocity is a vector quantity. This means that speed only tells you how fast an object is going, but velocity tells you how fast the object is going and its direction of motion. But what does this mean? In one dimension, the only difference you will see is that velocity can be positive or negative, while speed will always be a positive number. And because of this extra information on direction, velocity is used most often in all physics calculations. Now let's look more closely at the math behind velocity, since there is a very good chance that this will be on your tests or exams. If there is a change in position with a change in time, then we can say that the ball has velocity, and we can turn these words into an equation. Delta x over delta t is equal to v. And notice how here we are showing vector quantities with lines over the symbols, but you might also see this shown in a different way, such as with symbols in bold. The simplest case is when the ball moves with constant velocity. You may be wondering why we are graphing position and not displacement here. They are equal in this case, since we're talking about total displacement. But be careful, this isn't always true, since you can talk about the displacement between any 2 points you want. Let's take a look at what constant velocity looks like. We can see that the position changes by the same amount for every time interval by looking at the position graphed against time. It is a straight diagonal line. What then would the velocity graph look like in this case? One trick you can use to predict what the velocity will look like is to calculate the steepness, or slope, of the position time graph. To calculate the slope, we can just look at the rise and divide it by the run. Let's try it out. We can see that the rise is going to be equal to 30 centimeters, since we start at 0 and end at 30. But now look at the run. We are starting at time 0 and run the experiment for 10 seconds. So the run is 10 seconds. 30 centimeters divided by 10 seconds is equal to 3 centimeters per second, which is the velocity. We found the velocity just by looking at the slope of the position versus time graph. So why are we allowed to only look at the starting point and ending point and forget about everything in the middle? Well, this is because the slope or steepness of the line never changed. It's a straight diagonal line from start to finish. No matter what part of that straight line we look at, the slope is always the same, so the ball must be traveling at constant velocity. Let's see what the velocity graph looks like now. It's a straight horizontal line. To make things easier to see, let's stretch out the time axis. But now let's speed things up and see what happens to the graphs. Consider how the slope of the position graph is steeper, and the value of the constant velocity becomes larger. Let's try that again with an even faster ball this time. It's even steeper now. So when we look at the slope of the position graph, we can figure out the velocity of the ball. But what about when we look at the slope of the velocity graph? Well, it turns out that we can actually figure out the ball's acceleration, represented by the formula delta v over delta t is equal to a. And since the rise here is 0, and 0 divided by any run of time is 0, we know that the slope must be 0. We never gained any velocity as time passed, so the acceleration is therefore constantly 0. But if the ball is a changing velocity with passing time, then the ball must be accelerating. Now we're going to have to look at an entirely different example.